Hey, welcome back everybody. We are going to kind of get into the thick of it with testing. I'm going to give you good news and bad news throughout this conversation. I posted a couple of extras for you guys to look at. The one that would be supplementary to this class is kind of the decision theory stuff. I didn't go into minimax estimators, but they're the estimators that you get when you find estimators that minimize the maximal risk. So every estimator has a risk function attached to it. It's a function of theta, and it will have a maximal risk. So you might say if you're a dam builder or something like that. So if you're going to replace the dam over that Hurricane Katrina wiped out, you might want to think about what's the most extreme event that you're going to see and build a dam to protect that. So I want people that are building infrastructure to do things that are maybe minimax. So if you're a nuclear engineer and you're in charge of, a nuclear facility, I want you to think about the maximal air that you have. Saying that, if you go to a casino or something like that and you're gambling, you don't need to think about maybe the maximal risk. What you maybe want to do is be good on average. So it kind of depends on what you want to do. So the casino is trying to beat you on average. And the probability that you wipe out the casino, it's not a big deal because they have insurance. So the insurance company might be following a minimax principle, but the casino itself is following maybe a Bayes risk sort of analysis. They want to do well on average. There's some guarantees that you can get with minimax estimators. There's also some guarantees that you can get with Bayes estimators. And so one of the lectures that I put up for you discusses that. I think on the final, we'll do a take-home final again, follow the same format, and I'll ask you a few relatively difficult questions. I'll give you a couple days to do that problem as well. So you won't get a full week like the last one. So it'll be business as usual. Finals week will be a lot of work. So, but I'll ask you, anywhere between 5 and 10 questions. So maybe 7 or 8 like I did on midterm 2. I thought that was reasonably successful. I haven't finished grading everything, but I got through half. When I was looking at questions, I think it really did prompt you to think about what we've been learning in class. And I can gear up some of those problems just to really jog what you know about the materials. So we'll follow that same format. I'll probably ask you a few decision theory questions there, so those lectures can help you. Everything I gave to you about hypothesis testing, I intend to cover in our last 4 lectures. So we're going to get on with it and go through all of that. I just thought I would give you a preview of what it looks like. So if you want to skim through those are available. That's always true, and there's some other lectures too. But there's quite a bit that's different between Bayesian testing and non-Bayesian testing methodologies. So we haven't really talked about any strict criteria. We're going to be getting into some strict criteria right at the end of this lecture with Neyman-Pearson. So the Neyman-Pearsonians are the ones that are trying to shield you against error rates. Unfortunately, they have to make some decisions up front about which error rates are more important to protect. A Bayesian does something entirely different. And we'll be talking about that. My major punchline is going to be, you get to decide all by yourself what sort of methodology you want to follow. What I hope to instill in you is at least an explanation as to why you might pick one over the other. So I think that lots of different testing methodologies are reasonable. It's just a question of, are you explaining it properly, and are you deciding something that's reasonable for the problem at hand? Okay. I will say that since kind of statistics dirty little secret in hypothesis testing, and basically nobody really agrees with each other. So we're really testing something like, we're going to ask some question, maybe H0 is theta is going to be greater than some value theta naught versus H1 theta is less than theta naught. This test isn't highly contentious, but the sharp point null test is where everybody starts really disagreeing with each other. Anyway, we'll go through a likelihood ratio test statistic example. Again, we'll talk about power functions, and then we'll talk about what Neyman and Pearson prescribed. They thought they were doing Fisher a big favor, and it backfired in their face. So Fisher did not agree with what Neyman and Pearson advocated. I'd say that's probably the #1 misunderstanding that most stat students have, that they think Fisher was a frequentist when it came to testing. He was not. So Neyman and Pearson are the frequentists. They were trying to get Fisher a frequentist interpretation for what he was doing, and he hated it. So the question is what did Fisher like? It's hard to tell. So hopefully we've dispelled a little bit in this class about the branches of inference and what they're trying to do. Anyway, let's get on with it. Look at a couple examples, motivate what Neyman and Pearson said, and talk about the repercussions. I think next time we'll get into the proof of Neyman and Pearson as well. Okay, let's look at this example, just to talk a little bit more about likelihood ratio test stats. Say you've got some xi's that are coming from this distribution. The distribution is e to the minus x minus theta, where x is going to be bounded by theta. And this distribution looks like this. So just to test you guys, what distribution is this?
The shifted exponential?
Can you say it?
Shifted exponential?
Yeah, it's a shifted exponential, but there's no rate parameter here. So it's a shifted exponential with rate 1. So if there was a lambda in here, we need a lambda right there, and this would be a shifted exponential with a rate parameter that you'd want to estimate. We're just going to be estimating the shift parameter here. Now, I will say that if we did have a rate parameter right over here, some of the xi's would be sufficient for estimating that parameter, but we don't have that over here. And the minimum is the minimal sufficient statistic for estimating the shift parameter. And so hopefully you can start seeing the factorization here. So let me just write that down, just to point this out. If our problem looked like this, e to the minus lambda x minus theta times lambda, then what I would say is sum of the xi's, I goes from 1 to n, would be sufficient for lambda, and x1, that's the minimum of all of my x's, would be sufficient for theta. And if you're like me, you're rolling the factorization theorem in your head, you're producting this thing up and thinking about all of this as a function over the parameters that you see. So this is just going to be lambda n e to the minus lambda sum of the xi's minus n theta. And you would notice that there's nothing I can do to factorize that away from that. So sum of the xi's is sufficient for lambda, and thinking about this right here, I probably want to write down that my indicator function x1 is going to be greater or equal to 15. And so this would be my factorization component for estimating n. Of course, if I were doing a maximum likelihood estimate, then I would want to look at this chunk 2, that there's a theta right over there, and n has something to do with it squashing that thing, as you see bigger and bigger values. Longer.
So here, like in the example that you just gave, we have 2 parameters.
Yes.
I don't know if you had just explained it, but why do we have the sum is sufficient for lambda and the minimum is sufficient for theta?
Easy data. So if I just factorize this, so this is going to be lambda n e to the minus lambda sum of the xi's.
Oh, I see.
E to the plus lambda theta And x1 is going to be greater or equal to theta. So what I do real quickly, once I factorize this, is I just look at the parts that I can't untangle. There's no data in here. There's just n. I'm not going to consider that data itself. So I just think about where the data can't be factorized away from the parameter. So I have two pieces right here. So this tells me that x1 is sufficient for theta, and this bit right here tells me that some of the xi is sufficient for lambda.
Okay.
That's what I do usually real quickly in my head when I look at a distribution, is I just imagine producting the thing up and what I can't factorize away from certain parameters. So kind of the quick grad school, you know, I'd say second year grad student way of doing factorization theorem. Yeah?
Yeah, I understand if you see the sum of xi and the minimum, they together is sufficient statistics for the two parameters.
That is true. Yeah, they're sufficient for the two parameters.
Yeah, how do you say that they are individually sufficient statistics?
Just by what I've just done, right over here. So, what can't I untangle from theta? x1. What can't I untangle from lambda? Some of the xi's.
So the middle part, we can just throw it.
Yeah, that would be my constant, right? It's all the little constant that I could soak into hx.
But it is a function of parameters, right?
Yeah, but it's just a question of which parameter. So if I were just thinking about lambda, let's say I knew theta. Theta was given to you and known. This is all part of the constant. So this part right here, I'd have to soak into here, but it doesn't have any data into it. And so if I knew what theta was, this would be the part that I would be thinking about. And then this part would get pulled into, that would be part of my constant. This would be along with that right here, but there's no data there. So this is the only place for data. I'll let you think about it a little bit more. So it's the constant part's the part that doesn't matter. So, and it's really, you know, you could break I could reintroduce the factorization theorem and say it breaks into 3 parts. You know, they ended up breaking it into 2 parts, where I would say the important part is this right here. This is also a function of just the parameters that go data in there. And they didn't write it down that way. Anyway, that's how I do the factorization theorem. So you can think about that. And I kind of like this example because it's got the 2 parameters in there, and then I can think about things. Let's simplify the example and just look at this. This is in your book. And so we know that basically what we just said is x1 has to be greater or equal to theta. This is my min sufficient thing. So let's just write down the likelihood function. For the likelihood, put that over here. We've already done it. Get rid of those lambdas. That's not part of our problem. Or a likelihood function. And if I wrote this down, I would know I've got a problem because I don't see anything that's not factorizable. I need to write down my indicator function that all of my xi's are greater than theta. And this will just be equal to e to the minus some of the xi's plus n theta. I'll write it down like that. And then this is going to be the indicator function that x1 is greater or equal to theta. And I can draw this. So now when I'm thinking about this as a function of theta, I'm thinking that theta is bounded by x1. Where before we were looking at it, the xi's were bounded by theta. I'm just going to write down, let me give myself a little bit more room. Let's say x1 is right there. So if I'm thinking about this as a function of theta, this is the part that tells me what is min sufficient. And I'm kind of rolling maybe that theorem where I'm looking at that ratio for mid-sufficiency, and I can verify real quickly in my head that everything else cancels out of that ratio, and this is the only part that would be actually in that ratio that I'd be thinking about. So I'm kind of employing those theorems in my head. But this part right here is telling me a little bit about the asymptotics of the problem. It's telling me as a function of theta, this function is increasing right here. Because this is e to the plus n theta. So that thing is increasing. It looks like this. Can't get bigger than x1, but it's increasing all the way until I get there. It's not asymptoting into there. Some actual value right there. This is going to be my likelihood function. So I'd say this is the part that I'm looking at when I'm thinking about my maximum likelihood estimator. Increasing until I hit this boundary right there. So this is the MLE. Okay, let's do some testing. We don't have real principles yet for testing, but we've at least thought about this measuring tool called the likelihood ratio test statistic, and I kind of like this measuring thing. So it ends up looking at the ratio of two maximizations. So this is going to be the max of theta over my null space. Divided by my maximum over my entire space. I'll just write it like that. I was writing down before that this would be an element of H0 and H1. These two things, that's really the whole real number line. So this right here is just minus infinity to infinity. So I'm just going to suppress that and say we're maximizing over theta. The denominator of this is always solving for an MLE. So same likelihood function that we're talking about. And I can write this thing down. So once I solve for these maxima. So this one's easy. That's just going to be the likelihood of x1. Give it all my data. This one's a little bit harder to think about because there's a couple cases that we have to consider. So let's just think about this real quick. That if theta naught were over here, so if theta naught is less than or equal to x1, then the maximization is going to be the likelihood evaluated at theta naught. Give it x. And we can just look at our picture. Where would this be maximal in the null set? Well, it'd be that one right there, because it's likely the function is increasing. And if x1 were greater than theta naught, then we would have that. That our maximum would be obtained at the boundary point. And so that's just going to give us lambda x is going to be a 1 if x1 is greater than theta naught. And if theta naught is less than or equal to x1, then we're just going to have this ratio.
I think for the second one, you put the values and the like the second inequality.
This one?
Yeah, they
Oh. Yeah, of course, right? Thank you. Yeah. Flip. Appreciate it. The hardest thing for me to do at 9 a.m. is keep my balance straight. Okay, so we can just write this down. This is going to be e to the sum of the xi's. There's a minus right in here, plus n. And I'm going to just plug in what this is right here. So this is going to be maximum over the null space right here. So this is going to be theta naught right there, divided by e to the minus sum of the xi's plus n x1, the minimum. There's a lot of cancellation. Let's just write that down. So if we solve this, if x1 was less than theta naught, you're probably not going to reject that null hypothesis. So, but if this thing is entirely small, then you might want to reject everything if you're in this setup right here. So keep in mind, you know what x1 is, and you know what theta naught is. It's given. So this is going to be e to the n theta naught minus, I'll write it like that, sort of breaks it there. And so ultimately, what we're going to show you is that Neyman-Pearson end up giving us a theory for talking about what this threshold is. But we've already discussed thresholding this, so some threshold. Our intuition is that if this value is very, very small, then we're going to want to reject the null hypothesis. The null is very unlikely compared to other values. We can simplify this just a little bit. That's just going to be x1. I'm just going to take a logarithm of both sides. So log of my threshold. I'll divide by n. I will just write down theta naught minus is going to be less than or equal to that. So I'm going to subtract off theta naught from both sides, minus theta naught, and then I'm going to flip this around. This is going to be a negative, and that will be a positive. So this is my criterion for rejection. This is reject if this is true. So if I see a minimum that's greater than this value right here, where I plug in whatever my threshold is, plug in whatever my null hypothesized boundary is, plug in n, this is my criterion for rejection. So this is called the rejection region. And that's a new term that we'll start using. So this defines, in terms of my data space, where I'm transforming over to the minimum, my criterion for rejecting the null hypothesis. Okay, so I think we get this example. It's just algebraic, but here's the real point that I'm trying to make, is that when I write down this criterion where I'm thresholding something, I'm really defining a part of the data space that defines if I see data that lives in that part of the space, then I'm going to reject. Eventually, we're going to need a real criterion for picking C. We're almost there. Let me show you another example. And I'll define power functions for you. This example is in your book as well. X, we'll say it comes from a binomial. And our number of trials will make this problem easy enough so that we can handle it algebraically. We'll say this is 5, and it's got a parameter theta. And we'll set up our hypothesis. So let's say somebody walked in and wanted to test this. They get to observe what X is, and they want to know which decision do they like better, the null or the alternative, H naught versus H1. Let's just take a step back real quickly. If somebody walked in with this problem and asked you to test this hypothesis, what would you say to them? Okay, try to read my mind. What would I say to them? You might say, all right, I'll do it for you. Warren?
Low sample size.
Yeah, maybe. So, possibly. I might say, can I get more data? Usually, if I say that to my clients, they don't come back. So, no. That's what I got. I spent $1 million flipping 5 coins. So, I can't possibly flip another one. I would tell them, could I not test this and just tell you what I think the data is? And what I would probably do is say, I'll even do a little bit better, I'll even quantify my uncertainty in what the data is. So I would not test. I would refuse to do it. I'd tell them what I think the data is. So, similar problem. You might say that there's a one-to-one analog for your testing procedures to what I do, but that's not always true. So, but I would say, this is a little bit artificial for me. I'm going to estimate data for you instead. So I don't like testing this sort of thing because we have to come up with a hypothesis, these thresholding values. Maybe these mean something to you. Maybe you're thinking, am I flipping a fair coin and I want to test this one? So maybe that is what you want to do, but I would say estimate data. If it's a one parameter inference, there's no need to do testing. So that's my own opinion. Saying that, it still makes a nice example to work through, see how these tests behave. So let's just say we're going to pick a rejection region. Our rejection criterion is if we observe X is equal to 5, we'll reject. I just made this up. The book made this up. So it's at least sensible. If I said something like, if X was equal to 0, I'd reject. It doesn't make any sense in this case. So, because it actually favors the alternative hypothesis and not the null hypothesis. So at least, if X was equal to 5, so every time I flip that coin it was a success, then I probably don't believe this. So at least this criterion is going in the direction to reject this appropriately. I'll let you think about that a little bit. We'll look at another example that will help exemplify that. My point is that if I said X was greater than 3, 4, or 5, something like that, that would at least be a sensible testing criterion for this problem. But if I said X was either equal to 0, 1, or 2, that wouldn't make any sense. We'll come into some definitions soon. We would say that test is biased. At least this is an unbiased test. It's a little strict. definitions before I continue in this example. Let's just say in any testing problem, of the form H naught, and I'll just write it down like this. Theta is an element of some big set. And I'm just going to call that big theta naught. Okay, so this is my capital theta. It's just some space. And H1 is going to be theta as an element of the complement of theta naught. So I'll just write down that this is the complement. So in any testing problem, and this problem that we're looking at is of this form, there's two types of errors that we can make. I'll just draw a diagram. Let's say this is the truth. So the truth is either H naught is true or H1 is true. And ultimately, when we look at data, we're going to make a decision. And we can either decide H naught is true or H1 is true. Okay, if H naught is true and we decide H naught, we're correct. If H naught is true and I reject in favor of H1, we call this a type 1 error. If H1 is true and we decide H1, we're correct. There's no error. And if H1 is true and we fail to reject, that's the typical one-on-one language, i.e. I've decided H naught. Now, some people have a lot of problems with that language. We fail to reject H naught. If that bothers you, insert that. I'm ultimately going to say you've made a decision about H naught. So this is a type 2 error. We're going to talk about these two different errors in the context of this problem. Okay, so back over here. Let me tell you a little bit more about this. So I'm just going to write down the power function I'm just going to write it down as beta theta. It's going to be a function of whatever theta is. This is just going to be equal to the probability that X is a member of the rejection region, given theta. X is in the rejection region. In the rejection region, I'm calling it R. So in the context of our example, the rejection region is when X is equal to 5. Just to give you something concrete. So this is the power function. This thing right here has something to do with both of these errors. So this if theta is a member of the null space. This is H naught, and I reject, I've made an error. So it's this type of error, type 1. So if theta naught is true and I reject it, I've just made a type 1 error. This is type 1 error. And this is the probability of that thing. If I reject and the alternative is true, I have not made an error. So theta is a member of the alternative space. I'll write it down the same way that we wrote it down before. So this is just the alternative. H1, I didn't make an error. What's the probability of not making an error? It's 1 minus the probability of making an error. And this is that kind of error, a type 2 error. This is going to be 1 minus the probability of a type 2 error. So lots of language going on, but I think you've heard this before. Some people don't deal with type 1 and type 2 errors, so if you're maybe in the machine learning community or you're a student in computer science, maybe you talk about things like precision and recall. So there are 2 different ways of calibrating the same errors. If you tell me what n is, and you tell me what type 1 and the type 1 and type 2 errors are, there's a 1-to-1 translation between precision and recall. I'm not going to define those for you, but there are different ways of calibrating errors. You usually calibrate errors that way when you're forecasting something. So statisticians talk about it a little bit different. So type 1 and type 2 are not the same thing as precision and recall, but they're 1-to-1 functions of it. Here.
It's kind of like a confusion matrix. So, like computer science, would this be like a confusion matrix?
Yeah, exactly. So confusion matrix, exactly. So you might estimate what those errors are. Absolutely. So here's a concrete problem for all of this. We're going to write down what the power function is. We do that. So our power function, b theta, and I'll just tell us, is power. This right here is the ability to reject. Reject H naught. Oftentimes, just to maybe confuse you, a lot of times when statisticians are talking about this and they're talking about power, oftentimes they're talking about it in the alternative space. They're talking about the power is 1 minus the type 2 error. When they're talking about it that way, they're just confining their definition of power to the alternative space. We'll see why that's the case in a second. So our power is the probability that we reject. So this is equivalent to the probability that x is equal to 5 in our example, because that's our rejection region. And I can compute that. So this is a binomial problem, so I know what the probability that x is equal to 5 given theta. And so I should probably write down this is given theta right here. So this is going to be 5 choose 5. Theta to the 5. 1 minus theta to the 5 minus 5. And there's an easier way to write that down. It's theta to the 5. So that's our power function. We draw you a picture of it. weights into the null and the alternative. So this is going to be theta. Theta is really bounded between 0 and 1. Right here. And this is going to be my power. And it looks like this. Give myself some tick marks right there. So my power function looks like that. Right there. And I can compute what the power is at 1/2. Right here. This is going to be 1/2 to the 5th power. Right here. I've pre-computed this. This is a small number. This is 0.0312, approximately. That's a very small number right here. This is the null space, and this is the alternative space. So what this says is that if the null is true, the probability of rejecting it is very low. And the maximal probability is 0.032. And that's good. But it's not very high, the probability over here, compared to over here. So we want this probability to be going up as theta gets bigger and bigger, just by the nature of the problem. So saying that, if I wanted my power to be 1/2 of rejecting the null when the alternative is true, I need to look at a very big theta to get that. So I'll just write down this right here at 1/2. So say we want the probability of a type 2 error to be bounded by 1/2 right here. So we don't want to be making a type 2 error. When the alternative is true, we don't want to reject. Ultimately, that value is right here. This is going to be 1 minus 1/2. So this is just 1 minus my probability of a type 2 error. So my bounding on my type 2 error is 1/2. 1 minus this is equal to the power function. And so this is going to say that theta right here has to be greater or equal to the 5th power, the quintic root of this. So just keep in mind, where did I get this from? I plugged theta 5. Right over here. Let me write that a little bit bigger. So theta to the 5 has to be greater or equal to 1 minus the probability of my type 2 error. I'm bounding my type 2 error by 1/2 arbitrarily. And so I'm just writing this down. This is equal to 1/2 right here. So theta has to be greater or equal to 1/2. And I take the 5th root of that. That number is very large. This is about 0.87. You can verify that. So if I want my type 2 error to be relatively low, which we want all our errors to be low. This is really low in the null set, but in the alternative set, I need theta to be at 0.87 if I'm going to bound my type 2 error by 1/2. So theta would have to be relatively large for this test to have a small type 2 error. Let me show you another rejection region. So let's consider a slightly different test. And we'll compare these two power functions to each other. Here's another test. and I'll say x is equal to 3, 4, or 5. I'm going to let this be the new rejection region. And I can work out the power function for this new test. The power function, b theta, and I'll just call it b star theta, just to denote that this is a different power function from the one that we just wrote down. So this right here is going to be b theta. This is a different power function pertaining to this rejection region. And this is going to be 5 choose 3. Theta to the 3, 1 minus theta to the 2, plus 5 choose 4. Theta to the 4, 1 minus theta to the 1, plus 5 choose 5. Theta to the 5, 1 minus theta to the 0. So slightly different. And I could draw what this looks like. So let's just look at what this looks like when theta is equal to a half. So when b theta is equal to a half, this thing is equal to all of these things right here. That will be a half. That will be a half right there. So this is going to look like 5 choose 3 plus 5 choose 4 plus 5 choose 5 to the theta to the 1/2 raised to the 5th power. So I'm plugging theta in for a half, and I can factorize that out of everything. So this right here is 10. This is 5. This is 1. So this is 16 times 1 over 16.
Is that
Nope, 32.
is that b star theta?
Yes. This is a half right here. So this kind of goes hand in hand what I was saying, that maybe we want to consider if x is 3, 4, 5, because it helps to balance these air rates out. So my new test has power 1/2 right at this boundary. And the power function looks like this. You can plot that for yourself. So this one is b star. Here's what I want to point out, is that we're making a few more errors over in the null region. So this has a higher error rate, but we get a trade-off. That this is better, that in the alternative space you want to reject more often. And so the power is higher over here for our second test than it was in our first test. But the errors that we make over in the null space is the trade-off that we make for getting those more desirable power functions over in the alternative space, i.e. this has a lower type 2 error over in the alternative space. So there's always going to be this trade-off. And I think we all knew this to start with. So the trade-off is as type 1 errors go down, type 2 errors go up. So the type 2 error is 1 minus the power function in the alternative space. So there's always this trade-off. So Neyman-Pearson proposed to do something about this problem. And you can kind of imagine there's an infinite number of things you could do here. Anytime there's a trade-off, there's something, there's all kinds of things you can do. And so Neyman-Pearson tried to convince us that this is the right thing to do. So Neyman and Pearson say fix the type 1 error. So fix or bound the maximum. Like in this example, type 1 error rate is a function of theta, but it's bounded by some number. So for our first test, the maximal type 1 error rate that I can make is about 3%. So we're actually going to fix that maximum that we're willing to occur. So fix or bound the maximum of the type 1 error rate and minimize the type 2 error rate. It could have gone the other way around. So they place a little bit more importance on the type 1 error rate. So that might be an arbitrary decision. I've heard this defended a lot. That, well, that's the thing that you're asking the question about, so that's the one you're more concerned about. But there is an imbalance as to how these things are being treated. So they're going to fix the maximum type 1 error rate, and they're going to try to minimize the type 2 error rate. It's the idea of the test. It might be desirable that you say, well, maybe I'll just try to minimize both of them. But what I just showed you with this trade-off is it's not possible. So you can't minimize both of them. You need to fix one of them before you minimize the other one. And so what Neyman-Pearson end up showing is that this likelihood ratio test statistic does this for us. And this is a cool mathematical result. So I really appreciate what they came up with. We'll discuss the utility and when this can be abused. But they showed us that the max data element to the null of the likelihood divided by the maximum of the likelihood in the unrestricted space, thresholding this does accomplish it. So what they do is they choose C to maximize, I'll say to bound the type 1 error. So we could do this with any criterion that we came up with. We could pick some thresholding thing so that we bound the type 1 error. But what Neyman-Pearson showed us is that when we pick C to bound the type 1 error, there's some sort of an equivalency between picking this thing right here, whatever that max is, and picking C. So there's going to be a one-to-one translation between those. So I can pick C so that I bound my type 1 error rate. So if I pick C to bound the type 1 error rate at 3%, 0.0312, that would end up, if I solve for x, it would tell me that x needed to be 5. We'll back solve for that. We'll look at some examples of this. But the cool thing that Neyman-Pearson showed us is that using this criterion, and this is the only criterion out there, is the one that minimizes the type 2 error. And so this test statistic is not arbitrary. There's real reason for picking this test statistic. So we'll come back and we'll prove that next time. So again, what I said is we'll pick C to bound the type 1 error rate. We can solve for x in this equation so we can figure out what our rejection criterion is. And this ratio itself automatically minimizes the type 2 error rate. So usually in all these p-value calculations, you you have some test statistic that you're forming a p-value based off of, but that test statistic is derived from the likelihood ratio test stat. And that's what most people do. If you came up with a p-value that was based off of some other test stat and it wasn't derived from the maximum likelihood ratio test stat, it would be beatable in terms of type 2 error. There would be some other test statistic that I could use to bring down the type 2 error. So it's only test statistics that come from the max likelihood ratio test stat that minimize the type 2 error or fix type 1 error. That's a lot to think about. Let's come back, write down formally what Neyman and Pearson said, and then we'll try to prove it. So if you want to have a look at that proof, keep